Hi, everyone. I'm Steve Douglas, Head of 5G Strategy here at Spirent Communications, the industry's leading test and assurance vendor for the ICT industry. And I'm very happy to be here today at the Tommy Flowers Network Virtual Summer 21 conference event sponsored by BT and NextG Works. Today, I'm going to discuss the 5G network digital twin and its role in accelerating industrial digital transformation. So let's get started. Firstly, for those who maybe don't know who Spirent is, I thought I'd give you a quick introduction. We're a global leader of automated test and assurance solutions for the ICT industry. And our solutions are used right across the development to live network operations lifecycle to help accelerate time to market through immersive network emulation and testing, to help realize efficiencies through intelligent lab and test automation, and to finally assure network performance and user experience through continuous and active testing in the live environment. So what is a digital twin? Well, there are many different interpretations and definitions of a digital twin out in the market today. But fundamentally, I think of a digital twin as much as a philosophy and of how it is implemented, a philosophy of having a digital replica or an emulation of a physical entity using real or simulated data to visualize and then to stimulate how that physical entity should or could perform and behave. And you may ask yourself, why would you want such a digital twin? Well, it offers designers, developers, and operation teams a cost-effective and flexible environment. In some cases, it's to accelerate R&D processes and increase productivity. In others, it's used to reduce risks by safely testing those damaging what-if scenarios and cyber attacks. Digital twins can be used to optimize decision-making by modeling unlimited configurations and combinations, or used simply to continuously improve reliability by identifying design weaknesses and mitigation opportunities. And to be honest, digital twins are not a new idea. They've been used in many industries and environments over the years. In aeronautics, they've been used to create virtual replicas of physical airplane parts and stimulate and simulate how they will perform. In shipbuilding, they're used to help optimize the design, maintenance, and production of real ships and subcomponents. And in the space industry, NASA has been pioneering digital twins for decades. Initially, they were called a pairing technology, and it was to simulate systems in out-of-reach environments such as space. So what's the link between 5G and digital twins? Well, firstly, more and more physical assets are becoming connected through communication networks so that they can be monitored, maintained, and controlled. Now, the evolution towards 5G with its extreme high speeds, its ultra low latency, and the support of massive machine type communication provides a perfect solution for physical asset digitization. And this connectivity is becoming a fundamental part of physical assets' underlying designs and their behaviors. Now, this means that a traditional digital twin of the physical asset now also has to or needs to be able to model the 5G connectivity itself and the communications environment it exists in. Now, for an example, if the physical asset's behavior is dependent on, say, ultra low latency communications, so it can be controlled remotely, or it is dependent on a large volume of communication centers, so it can be monitored, then these aspects of its makeup, they need to be modeled to help optimize the design and to continuously improve the effectiveness of them in the field. Finally, digital twins will need the robust connectivity which 5G promises to actually interact with the physical assets. Now, this connectivity will need to cover a range of capabilities, from securely transferring large volumes of data to delivering reliable and deterministically low latency. So I suppose the question is, why do we need a 5G then digital twin? You see, 5G is still in its infancy. Its universal availability is currently limited, and the technology is exceptionally complex. So just how do you test the real world scenarios of a network that currently only sees a small fraction of its future usage? And industries who are exploring the business potential of 5G, they need a flexible and cost-efficient playground, especially when many of these new use cases are unproven. And as we know, industries are notoriously conservative, both in nature and very much focused on the bottom line. Then there's the heightened risk around cybersecurity, meaning we need a representative sandbox to proactively research risk and model mitigation techniques. And finally, communication service providers themselves. They need environments to help them continuously validate and optimize the complex new 5G network and how it should behave and perform in the live environment. So let's meet the 5G network digital twin. It's an emulated replica of the 5G physical network. A sandbox, a playground under your control, fully flexible, configurable, and repeatable, not requiring precious spectrum or high-end network vendor equipment. It's software defined, it's upgradable, allowing it to seamlessly evolve with the industry standards. It can work integrated with real network elements or with other twins and simulators to allow continuous prototyping, testing, and optimization across a variety of potential situations to efficiently and proactively model and assure the 5G network and the associated services. Underneath the hood of the 5G network digital twin are three key capabilities. You have network emulation, traffic generation, and automation. Now, network emulators are used to provide the realistic digital replicas of the physical 5G network entities. Now, this includes the new and complex 5G radio with its new radio frequency ranges, antenna technologies, and functional splits. It also includes the 5G new core network with its service-based architecture, network slicing functionality, and disaggregation capabilities to the cloud and to the edge. Network emulators provide an environment to replicate the real system while providing enhanced modeling capabilities. And as I mentioned, these emulators can integrate the real network functions to provide a hybrid lab environment. Now, this is complemented by traffic and impairment generations and real-world record and playback systems to stimulate the environment with high-capacity traffic mixes, impairments, and what-if scenarios. Now, the traffic can be emulated to reproduce exact real-world scenarios and payloads or simulated to model future unknowns. Impairments can be added to stimulate how the environment behaves and performs when conditions change, as they do in the real world, such as higher latencies, packet loss, or even security attacks on the system. And finally, automation is used to intelligently manage the configurations and execution, creating a flexible, repeatable, and cost-efficient environment to accelerate R&D and increase productivity. Now, the best way to understand this is to look at a real-world example. Now, the example I'm going to share here is pioneering work, which is being done around connected and automated mobility with Warwick Manufacturing Group here in the UK. Now, the challenge is that testing on real worlds is extremely limited and risky, and that 5G networks are not universally available today. And there's a clear need to be able to replicate the complex driving scenarios, changing environmental conditions, unexpected events, and the behaviors of the communication network itself in a safe and repeatable environment. Now, here you see on the slide on the top, the 5G network digital twin cooperating with an advanced driving simulator to prove the benefits of 5G for connected autonomous vehicles and on-road management systems. Now, together, both the network twin and the simulator provide a replica of the real environment below, allowing it to be modeled and emulated on an ongoing basis, and providing an opportunity to look forward in time and to consider that what-if future planning. The driving simulator itself on the very top left-hand side is a 360-degree photorealistic environment which hosts a real vehicle inside an anechoic Faraday chamber, shielding it from the external live communications network. Now, the vehicle sits inside this environment and it's integrated into a vehicle dynamics, hardware in the loop, and video simulation suite, which allows the vehicle sensors, the onboard cameras, to think that it's actually in a real world environment. And with the 5G network digital twin replacing the shielded external communications network, the vehicle now thinks it's also in a real 5G network. In essence, these two connected twins become their own immersive environment, allowing researchers now to test how 5G communications network behavior could impact future connected driving use cases, how 5G network slices could be used to provide differentiated services for vehicle and passenger applications, and how different radio technologies and frequency ranges could be optimally used to provide critical coverage. And finally, determining how a connected vehicle would perform on a 5G network that millions of things and people are using at the same time, a near impossibility on today's live 5G networks. Now, the final example I wanted to give is also with Warwick Manufacturing Group, who have developed a unique configurable combination of real and synthetic environments and systems to enable testing, prediction, and analysis of devices, subsystems, and the emergent behaviors of subsystems in a way that is scalable, efficient in the use of resources, and controllably repeatable. Now, here you see an example of the environment used for industrial research, combining both lab-based controlled environments with live real-world systems and networks. The 5G digital twin enhances the lab-based controlled environment with emulation of both the 5G new radio and the 5G core for non-standalone and standalone testing scenarios. The ambition of this facility is to provide an environment to accelerate the research and implementation of 5G within industrial, private, and campus networks. You see, the potential benefits of 5G to enhance smart factories and manufacturing process is immense. 5G-enabled industrial IoT and private networks can play a pivotal role in industrial transformation, helping simplify the factory environments and its reconfigurability with secure and ubiquitous connectivity, and even a future potential to replace industrial Ethernet, or helping enable process monitoring and automation to significantly streamline operations. Now, this could lead to a potential 30% increase in factory efficiency, enabling new operating models and helping the transition from linear to circular value chains by cutting and eliminating waste, and helping enable optimizations across energy-intensive activities such as system maintenance, supply chains, and precision manufacturing. This again alone could lead to a potential 20% reduction in annual energy consumption and CO2 emissions. These are highly desirable economic and environmental outcomes, and a reason why it's critical systems like the digital twin can help model these environments to make sure that they can succeed and are continuously optimized. So to conclude, there's a quote from the Irish poet and playwright Oscar Wilde that says, "Imitation is the sincerest form of flattery." Well, this is more than flattery, as the 5G network digital twin is imitation without limitations. So thank you for your time today. Thank you for being invited here to speak by our sponsors, BT and NextG Networks. And I look forward to seeing you at the event and at some of the panels I'll be attending later on. Thanks for joining.